Okay, so yesterday we did this data table and we went through the June and December. On September 22nd, the fall equinox occurs, and this is easy for me to remember that the equinox is when the sun is directly overhead at the equator. And this is because the North Pole is not tilted either toward or away from the sun. It's neither. It's kind of going sideways. And the location that receives 24 hours of daylight is none. Nobody on our planet has 24 hours of daylight on the fall equinox. Everywhere gets 12 hours. And then on March 21st, this is called the spring equinox. And this is pretty much the same thing as the fall equinox. The Earth's North Pole is tilted neither toward or away from the sun, and the sun is most directly overhead again at the equator, and everywhere on the planet gets 12 hours of daylight and 12 hours of nighttime. So what we did in class today is we drew this diagram, and to make this a little bit easier, I'm going to draw this for you. So we're going to start off by drawing the sun right in the middle of your paper. And this is going to be on page 70, and you're going to want to turn your notebook sideways so that you have a really wide space, right? And you should have the spiral either at the top of your page or at the bottom of your page, and you've got a nice wide piece of paper to draw this on, okay? And so draw the sun in the middle about the size of a quarter, and then we're going to draw the Earth in 4 different positions around the sun. We're going to draw the Earth on the left-hand side, as far to the left on your notebook as you can get it. Notice that I tilted the North Pole and the South Pole so that we can see our axis is tilted, and the northern axis is tilted toward the sun, or toward the right-hand side of your page. We're also going to draw the equator, and we're going to label it EQ, so it stands for equator. And then we're going to go all the way around and label and draw Earth in these different positions around the sun. So here is the Earth in another position around the sun. Again, I tilted my axis so that the North Pole is tilted toward the right-hand side. I'm labeling my equator on my Earth. And I'm going to do another one on the right-hand side of my page. Now, we're not going to draw it all the way over on the right-hand side of your page this time. This time we're going to draw it a little bit closer to the sun. Because technically speaking, the Earth is a little bit closer to the sun at some times of the year, and a little bit farther away from the sun. It's not a big distance difference. I'm really kind of exaggerating it here. I'm going to draw my equator again, and notice that I've tilted the northern axis toward the right-hand side of your page. Okay. And then we're going to do the same thing up top here. We're going to draw another Earth, label our equator. I realize on my diagram it does look like this top one is a little bit closer to the sun than the bottom one. I did not mean to do that. It's just that this green spot, this little green bar up at the top with my words is kind of in the way. But yours can be equidistant from the sun, the top one and the bottom one here. All right, so now we're going to label each of these with their dates. And we're going to start with June 21st. So what you're looking for here for June 21st is which one of these has the North Pole tilted toward the sun for June 21st. Because the North Pole is always tilted toward the sun on June 21st. So which one is it? If you said the one that's all the way on the left, you were correct. So that one is June 21st. We're going to label it also as the summer solstice. And we're also going to point out where the sun is directly overhead. For who on the planet is the sun directly overhead? Should be at the Tropic of Cancer, which is 23.5 degrees north. So if I'm looking at my sun here and the main ray of the sun is aimed directly north of the equator right here, this would be the Tropic of Cancer. I can't fit that all on this line, so I'm going to abbreviate T-CAN for Tropic of Cancer. Okay, that's probably a little too far north from on my diagram, but that's okay. We get the point. All right, next, September 22nd. Where would that be? Well, it's going to be after the summer. So what we want to think about is, how is the Earth revolving? Is it revolving clockwise or counterclockwise? And if you said counterclockwise, you were right. So this one is next. So draw your arrow to the next one. Label this one September 22nd. We're going to also label this the fall equinox. And the sun is aimed directly at the equator. Okay? So for those people, the sun's rays are always hitting exactly at the equator. If this video is going too fast for you, feel free to slow it down or stop it whenever you need to. Next up, we draw our arrow. It's going to be this one. This one is December 21st, which is our winter solstice. First day of winter. The sun is aimed most directly at a special line of latitude that we call the Tropic of Cancer. Nope, I was wrong. Tropic of what? Capricorn. So I'm going to call it T-Cap. And last but not least is this last one here, which is March 21st. And this is our spring equinox. Because it's an equinox, I'm going to easily remember equinox. Sun is hitting the equator. Easy way to remember that. And then you want to draw one last arrow connecting the spring equinox over to the summer solstice. All right, the next thing that we want to label is, if this summer solstice is one day, this is June 21st, then that's the first day of summer, which means the rest of the summer is on one of these arrows. If this one is the first day of summer here, then that means the rest of the summer has got to be right here. So for example, if your birthday is July 4th, let's say, right? July 4th might be right about here, okay? Because June 21st is here. And then if this is the fall equinox, then I know that this arrow represents the fall. And if this is December 21st, then I know that this arrow represents winter, the season of winter, because December 21st is the winter solstice, which is the first day of winter. And if my birthday, for example, is January 4th, that might be right here. Okay? And then maybe later on would be February. By the time their movement hit March, here's March 21st, that's the spring equinox, first day of spring. And so the season of spring is right here on this arrow. All right, last thing we're going to label. I put these two dates, January 4th and July 4th, on here for a reason. These are special dates. January 4th, I would draw an arrow here. This is when the Earth is the closest to the sun. And we call that date perihelion. Perihelion is a special name. Helion actually means sun. Helios or helium is what the sun is made up of, and so that's why helium, helion means sun. Peri means about. So I'm guessing about as close to the sun? I don't know. And then the other date, July 4th, is when we are the farthest from the sun. July 4th, I know, is also Independence Day, but it's a total coincidence that we're farthest from the sun on July 4th. It's just a coincidence, the same day as our Independence Day in the United States. This day is called aphelion. There's that word again, helion, which means sun. Ap, or anytime you put an A or ap in front of something, it means not. So I don't know. We're not closest to the sun, I guess. I'm not sure how they came up with these words, but that's kind of where those words come from. So that is, in a nutshell, the seasons. Now, for me, when I was learning this, my first confusion came from this idea that we're the closest to the sun right in the winter time. Because I was like, wait a minute, if we're closest to the sun, shouldn't we be really hot? And that for me was the biggest understanding that, oh, okay, it doesn't have to do with how close we are to the sun, right? Because we're closest to the sun in our winter. So anybody up in the northern hemisphere experiences winter, but anybody in the southern hemisphere, it's not winter for them. It's summertime. So again, the reason we have seasons has nothing to do with the fact of us being closer or farther away from the sun, because that distance, to be honest with you, is not that big of a distance. You don't even notice it. Like, we've drawn it to make it really look different, but it really looks like we're the same distance from the sun all year long, if you were to actually look at it for real in outer space. It really has to do with the tilt of the Earth and how we revolve around the sun. And the fact that because we're tilted, certain parts of the Earth get more direct sunlight than other parts of the Earth. And that's it in a nutshell. So now you should be able to do the